So f of x equals the square root of x. I want to find the derivative of f, so I want to find f prime. So I'm going to state just my limit definition of the derivative function. Okay, first thing I want to do is find an expression that will represent what's in the numerator there. So we already know what f of x is. F of x is just the square root of x. So we're pretty good to go with that piece, right? So we just need an expression for f of x plus h, which just replace the x with x plus h. That's just root x plus h. Great. So as we become accustomed to, if you just try and immediately do a direct substitution for 0 for h, you're going to end up with 0 over 0. So it's going to be indeterminate. But in this case, there's not really much to simplify, right? Like I can't combine anything. These are radicals, and they have different radicands. You can only add or subtract radicals when they have the same radicand, meaning what's under the radical. But there's an idea that we've used every so often, especially when it comes to radicals that involve binomials, so two terms. Any idea in the chat about what I'm getting at? Yeah, conjugate pairs, perfect. So we're going to use this relationship that we know a plus b times a minus b comes out to a squared minus b squared, right? And so in our case here, the conjugate pair is going to be root x plus h plus root x. And I'm just going to do that in both the numerator and the denominator. All right, so keep in mind what's a and what's b. We have a as the first square root, b is the second square root, so it's going to end up being a squared minus b squared. So squaring those just gets rid of the square root, so I have x plus h minus x all over h times root x plus h plus root x. And I don't want to forget that I have not taken my limit yet. It's important. All right, so what happens? I can get rid of x's, right? Those cancel. And then all I have left in the numerator is an h, and I also have a factor of h in the denominator. So I can divide out an h here. My numerator just becomes a 1. So we have the limit as h approaches 0 of 1 over root x plus h plus root x. Well, now let's do our direct substitution. Just replace that h with a 0. We have 1 over root x plus root x. Now these do have the same radicand, so we can add them. We get 1 over 2 root x, right? So let's kind of state our final answer. F prime of x equals 1 over 2 root x. All right, and I'll show you that graph in a moment. But first, it asks us to find the domain of the derivative. So we have sort of two red flags when we're looking at this function for a domain. We have a square root, which can cause domain issues, right? When you have a square root, what sort of values do you always want under the radical? What do you want to make sure about your radical? Positive or 0, right? Because you can take the square root of 0. I agree. But we're also in the denominator, right? So what do we want to make sure about my denominator? What do we not want to occur? Yeah, not zero. Not zero. Dylan, that's an O. But I agree, not zero. So that means that our domain has to be positive and also non-zero. So 0 to infinity, not including 0 is my domain. Whereas the domain of my original function was inclusive of 0. Right? So I get a slightly different domain for my derivative. And the reason is, remember, yes, the derivative is a slope, but it's specifically defined as a limit of slopes. And for a limit to exist, it has to exist from both sides, right? Well, every single point on this graph, we can approach from both sides, except this point, right? We can't approach the slope from both sides of that because it's an endpoint. So the derivative does not exist at the endpoint, and thus it's discluded from the domain. All right, well, let's think about graphically, what do we expect this graph to look like? What can you guys tell me about the characteristics of this slope, or of these slopes? Yeah, and are they positive or negative? So the slopes are positive and they're getting less and less steep, right? They seem to be approaching 0, but they start off at their most positive. But at 0, it's not going to be defined, right? In fact, at 0, you're going to have what's basically almost a vertical slope. So you're going to expect the y values for your derivative function to be extremely large over here near the origin. And they're always going to be positive, but they're going to be decreasing towards 0, right? The slope is never going to get to 0, but it'll approach 0. So that's what I'm going to expect my f prime function to look like. And we'll graph that in GeoGebra to verify. But there's one more thing. I want to come back to that little idea I was trying to incept on you. Remember when I put the sleep machine on your arm and then I invaded your dream? And that's an Inception joke, guys. Have you not seen that movie? All right. We can rewrite the square root of x as an exponent, can we not? What's the exponent version of the square root of x? X to what power? Yeah. I can rewrite my derivative in the same way. So my derivative came out to 1 over 2 root x, right? Ooh, I'm getting a little crowded here. You guys are really getting to know me now. This is about how my board organization goes at school. I start from the middle because I think that's smart for some reason, and then I just have to I create a maze. All right. Well, 1 over 2 root x is the same as 1 over 2x to the 1/2, yes? Now I can move that x to the 1/2 to the numerator. You guys remember what you need to do if you want to flip a term to the other side? So if I have 1 over a to the n and I want to take a to the n and move it to the numerator, what happens to the exponent? Yeah. It's negative, right? So it's a to the negative n. So this is 1/2 x to the negative 1/2, right? Oh, you guys can't see that. Sorry. All right, let's do that comparison, that superficial comparison of our original function here to our derivative function. What do you notice? exponent became coefficient, right? What happened? What's the new exponent on our derivative? Yeah, it decreased by 1 again, right? All right, so maybe some more empirical evidence that that property might hold. We may eventually be able to find derivatives without having to go through this whole limit rigmarole. But not for a minute. Oh, can you guys not hear me? So now I'm just giving you a little more practice in a different setting. We're finding f prime if f of x equals this rational expression. I'm just throwing different types of functions at you. This definition should be memorized by now. It's really important. Okay, we already know what f of x is. We need an expression to represent f of x plus h. So off to the side, I'll say f of x plus h equals 1 minus the quantity x plus h. Really important that you replace that in parentheses because it's subtraction. So we have to remember to distribute that negative. So over 2 plus x plus h. I'm just going to simplify that to 1 minus x minus h over 2 plus x plus h. All right, so we're ready to get back to our derivative. So this is 1 minus x minus h, over 2 plus x plus h minus 1 minus x over 2 plus x over h. Right, so again, if you just at this point try to do the direct substitution of 0 in for h, you will end up with the 0 over 0. Anytime you have a fraction, like a complex fraction, so a fraction involving fractions in the numerator and or denominator, again, that's called a complex fraction, we want to simplify that to be a single fraction. That would always be possible to do. So first thing we'll do is just focus on that numerator and combining that into one term, one rational expression. So to do that, we need a common denominator, which can be found just by multiplying the denominators together. So in this case, our common denominator is just 2 plus x plus h times 2 plus x. So all I need to multiply is by whichever factor is missing. This one's missing the 2 plus x plus h. This one's missing the 2 plus x. Now they have a common denominator. I can rewrite the numerator of that complex fraction as a single rational expression that will have the denominator 2 plus x times 2 plus x plus h. All right, but I am going to have to expand out the numerator, the very top of those, which is going to be a little bit obnoxious. But you guys passed algebra and algebra 2, so you can do this as long as we're careful. So I'm distributing. I'm going like this, right? That's going to give me 2 minus 2x minus 2h. And I'm distributing the x. So it's going to be plus x minus x squared minus xh. All right, that's just the first piece. This one's kind of ugly, but we need practice in the ugly ones. Minus, open parentheses. Same thing on the other side. Distribute the 1. We're going to get 2 plus 2x plus 2h. Distribute the negative x. We're going to get minus 2x minus x squared minus xh. Okay. Now keep in mind that that entire set of parentheses has a negative in front of it right here, right? So that negative is going to distribute to all of those, and it's going to give me the opposite sign on all of those. So now I'm going to do the combining like terms. I'm going to keep that in mind. We're going to be extra careful here. It's these algebra steps that are easy to make like clerical errors on for a calculus student, because you're so focused on like the overall calculus idea that it can be, you get to this and you rush through and then you miss something. So just be careful. And I do it all the time. It's just that I get to have, 20 of you checking my work at all times to call me out on it, and you guys don't have that luxury. All right, so I have a constant. I have a 2. Are there any other like terms? There sure are. There's this 2 and this. Right. So I can cancel the 2. I'm going to try and kind of go in order here. So I have negative 2x plus x. So that's negative x, right? And then in the parentheses, so I have negative x, and then this is going to be a positive 2x, isn't it? You guys agree with that? So negative x plus 2x gives me x. All right, so I've dealt with that, I've dealt with that, I've dealt with that. All right. Moving on, negative 2h. Any other h terms? I got this one here, right? Which is also negative 2h. So negative 2h minus 2h is minus 4h. Okay, I dealt with that. I dealt with that. Oh no, I missed one of my 2x's, didn't I? All right, so that should also be, we should take away another negative 2x. That makes this negative x. All right, we got x squared. And this is going to end up being positive x squared, so those cancel each other out. And then we have negative xh. This is going to end up being plus xh. So those cancel each other out. Is that right? And I just realized this should all be over h. I probably should have done this in an extra step. I got lazy, guys. I didn't want to take the time to distribute that negative, and now I'm afraid that I made a clerical error. So if you see something that I did, let me know. What I'm getting is negative x minus 4h. That's all over 2 plus x over 2 plus x plus h. And we still have that all over h. And I can put that h over 1, so now I have a fraction divided by a fraction. Yeah, I sure did screw something up. God damn it. I left something out. Hold on. Paused my recording, luckily, so if you have to go back and view this, you won't have to see the mistake that I made. All right, so now we get the limit as h goes to 0. We have negative 3h over that common denominator of 2 plus x times 2 plus x plus h. And we'll flip that second fraction and we'll multiply. We'll notice, yes, we can divide out the h that's common to the numerator and the denominator. We're now left with negative 3 over 2 plus x times 2 plus x plus h. And we should now be able to make our direct substitution of 0 in for h. And we get negative 3 over 2 plus x times 2 plus x, which is the same as negative 3 over 2 plus x quantity squared. So I'm just going to kind of finalize my answer. F prime of x equals negative 3 over 2 plus x quantity squared. Boy. That one was difficult, and I went ahead and made it much harder for you guys. So apologies for that, but good looking out for my clerical errors. I'm gonna verify in GeoGebra that this makes sense graphically. GeoGebra is also something that is free for you guys. It's a Google app. So if you go to geogebra.com, this is a good thing to have, you know, just as you're kind of doing your homework. It makes it easy to check problems like this. All right, so we had our original function was just 1 minus x over 2 plus x. And f prime great, and it'll give you the algebraic version, which is exactly what we have. They just multiplied out the 2 plus x quantity squared, right? So that kind of helps us verify our solution. You can see that all of these slopes, right, are negative. Like if you look at the tangent slopes on this side, they're all negative, and the tangent slopes on this side are also all negative. So all of our y values on our derivative function are always negative. All right, now the fun stuff. So notation is huge in calculus. You've already been kind of confronted with some brand new notations, namely the limit notation. And then the other thing you've had is this derivative notation that we called prime notation. Prime notation is okay, but oftentimes the preferred notation is what we're going to call Leibniz notation. Named after Gottfried Leibniz, who simultaneously discovered calculus at the same time as Isaac Newton, and they were huge rivals. So what does this notation mean? Well, again, in the chat, what's a derivative? It's a slope. In algebra, you guys saw that notation? Do you know what those little triangles are called? Yeah, that's a capital delta. So it's delta y over delta x, and it just means change in y over change in x. But that delta means specifically there's a finite change. You're finding it between 2 points, right? So Leibniz kind of went along with this, except that remember that when we're finding a derivative, we're no longer finding a slope at a single, or at between 2 points, we're finding the slope at a single point. So rather than being a slope between a finite change in y over a finite change in x, we think of it as a infinitesimally small change in y over an infinitesimally small change in x. Right? And that produces our slope at a point. And so what Leibniz did was go, I'm going to use kind of a lowercase delta. Which eventually sort of just morphed into an italicized d. But like if you look in math texts, you'll often see it written as like, it'll look more like a lowercase delta, which is kind of has this flare. Oops, not dx, dy. Kind of has that flare to it. Does that make sense? But the idea was, oh, okay, well, if capital delta is a finite change in y over a finite change in x, lowercase delta can be a infinitesimally small change in y over an infinitesimally small change in x. And so there are a bunch of different ways that we can think about that. We can think about it as dy dx or df of x, since y and f mean the same thing. Or we can write it like this. Here, it works kind of as an operator. All I really did was take the f out of the numerator. It means the same thing. An operator? An operator is what I meant. But this is useful for us. Whereas prime notation doesn't really work as an operator. It works as a definition, right? So if I told you that your function was x cubed minus x, like in our first example, f prime really only works as defining the derivative once you've figured out what that is, okay? So once you know what it is, oh, it was 3x squared minus 1. Great. Prime notation works great. But in math, sometimes we want to be able to do things in steps, right? We want to be able to simplify in steps. So like way back when you guys were in 4th grade and you were just doing PEMDAS type problems and you had like x, or no, I guess you weren't working with algebra in 4th grade. You had like 4 minus 2 squared plus 7. And you couldn't do all that in your head. You have PEMDAS, right? And you have these operators that kind of allow you to understand the order in which to do them. Once you do that operation, the operator gets dropped. Does that make sense? So the first thing you do here is you would deal with what's in the parentheses. You would subtract 4 minus 2. You go 2 squared. Well, now I no longer have a minus sign because I've done that operation. Okay, then you would go exponents and you would square and you go 4 plus 7. And now I no longer have that operator of the exponent because that's been dealt with. And then I get 11. I no longer have a plus sign, right? That is sort of how the operator of Leibniz notation, the ddx, works, okay? It works like an operator, but for a derivative. It's basically saying, take the derivative of whatever's in front of me. And once you move it through the expression, then you've taken the derivative. So let me show you kind of what I mean. And we'll hit this hard in a few segments, but let's go back to this idea of the first example. What I wanted was the derivative of the function y with respect to x, right? I wanted dy dx. Well, another way of saying that is df dx, because y and f mean the same thing. Well, another way of saying that is d dx of f. You're not always going to have to write out this many terms. I just want to be really clear about the equivalence and where it goes from being the definition of a derivative to an operator. Right now, I've now kind of converted it to an operator where I'm saying, okay, take the derivative of f of x. Well, f of x is x cubed minus x. And so now what I'm trying to do, you can think of moving that derivative through the expression, and kind of as it wipes across the expression, you're going to take the derivative of each individual term. That's not a property we've explicitly defined yet. I'm just getting you ready for it. It's going to come. And so when you think of that, think of this derivative sweeping across there, and you would go, oh, okay, do the math, find out, oh, the derivative of x cubed is 3x squared minus, oh, I still have to take the derivative of x. Does that make sense? So notice that once I took the derivative of the first term, there's no longer the ddx in front of it. Now I'm just worried about taking the derivative of the second term. And then you could go through, do the calculus, and find out that the derivative of x is 1. You would end up with 3x squared minus 1. There's your overall derivative. Now we can define it using prime notation. So I know it's a lot at first. We'll get used to it. One thing I will say, when you are using it as an operator, the Leibniz operator goes in front. When students first start using it, I'll forget to remind them of that, and they'll write like something like that, and it makes my eyes hurt. Because it would be like the equivalent of you're trying to add 3 plus 5 and you wrote down this for me. All right, go ahead and add 3 plus 5. And I'm like, I get it. I get what you're going for there. I don't like looking at it. It's not the accepted form. So when you use the Leibniz notation, it goes in front of the thing that you're taking the derivative of. If you're confused, that's okay. We're going to hit this hard. It'll sort of be trial by fire. Higher derivatives. The second derivative. You can take a derivative of a derivative, right? So, for example, first example we did, f of x was x cubed minus x. The derivative was 3x squared minus 1. Since this is just a function, I could take the derivative of it, and then I'd be looking at what we call the second derivative of x. So I could just apply my derivative definition to that, and then I'd be looking at the second derivative. The prime notation for second derivative is pretty intuitive. You just put another tick mark. The Leibniz notation, I will agree, is not intuitive at all. But what you want to think about is you are taking the derivative. So remember, d dx means it's the operator. Take the derivative of what's in front of me, and you're taking the derivative of the first derivative, which in Leibniz notation is dy dx. An operator is just a thing that it performs an operation in math, right? So the operators you guys are used to, plus, minus, multiply, divide, raise to a power, plug a function into another function. That's a type of operation. So now we're defining take a derivative as an operation. All right, and then the Leibniz notation for second derivative becomes this. Now, this is a little unconventional and might be ugly to you, I agree. But if you look at it in terms of what's going on here, how many d's do you see in the numerator? Right, we see 2. And then notice that both denominators are dx. So it's dx. It's actually quantity squared, but by convention, that's not the way we write it in math for some reason. It's frustrating. Most of math is extremely consistent in its like notation conventions. This one is not that consistent. All right, so what if I was going to take the third derivative? in Leibniz notation, I would take the derivative of, right? This means take the derivative of the second derivative. What do you think that would look like in the chat? D3y in the numerator over dx cubed in the denominator. So anytime you put d dx in front of something, it means take the derivative of this thing. All right, we just got a few slides left. Find and interpret f double prime of x. So notice this is the original function that we used from our first example. So we already have f prime. And this comes from our first example. It was 3x squared minus 1. All right, so I want f double prime, which means I want to take the derivative of 3x squared minus 1, right? All right, well, I'm going to use my limit definition. Limit as h approaches 0. I need an expression for f of x plus h, which is just going to be 3 times the quantity x plus h squared minus 1, right? And then an expression for x, f of x is just 3x squared minus 1. So that's going to be what goes into my numerator. All right, so it's going to be 3 times x plus h quantity squared minus 1 minus the quantity 3x squared minus 1 all over h. Okay, this time I will not be tricked into trying to take the shortcut. I'm going to expand this completely. So I'm going to have 3 times x squared plus 2xh plus h squared minus 1 minus 3x squared plus 1 over h. We'll go ahead and distribute our 3. We'll have 3x squared plus 6xh plus 3h squared minus 1 minus 3x squared plus 1. Everything is over h. All right, let's get rid of our like terms. So we have a positive and a negative 3x squared. We have a negative and a positive 1. Leftover terms all have at least one h, so I can divide out that h. And I'm left with the limit as h goes to 0 of 6x plus 3h. Okay, direct substitution of 0 in for h. We end up with just 6x. So f double prime of x is 6x. All right. There's my original function. There's my f prime. The y values of f prime represent the slopes of the original function f at that x location. Here's y double prime. 6x, just as we thought. And so the y values in the purple represent the slopes of the orange at their corresponding x values. So take a look here. On the orange, the slope would be 0 right here, flat slope. So the y value is 0 for the purple. Over here, are the slopes positive or negative on the orange? On the right-hand side. Positive or negative slopes? Positive, and the slopes are increasing as you move up, right? So on the purple, positive y values and increasing. On the left, negative slopes, but getting closer to a slope of 0 as we move towards the right. So negative slopes that start out very negative, but get closer, negative y values that start out very negative, but get closer to 0 as we approach 0, okay? So the second derivative are just the slopes of the first derivative. All right. I got one more slide. Let me just make sure. All right, the other thing they're going to ask for is they want you to be able to work backwards. So this is one I stole from Khan Academy. And so one thing you should be able to do is be given a limit, and you should be able to identify the function and at what point they're asking for the derivative, right? And you can do that by comparing. You can compare it to, remember that f prime at a is the limit as h approaches 0 of f of a plus h minus f of a over h. Or, and we haven't revisited this one in a while, the other way to define it is the limit as x approaches a of f of x minus f of a over x minus a. Those give you the same thing. So a type of problem you can see is they give you the limit and they ask you to kind of work backwards and try and figure out what the derivative that they're talking about is. And so when I look down here, the easiest way I think to do this is first to find out what a is. What's the value of a? What's the thing that they're adding to h? So in this case, what are we adding to h? Right, 9. So a is 9. And then it's clear that they're using the first definition, right? They're using the h approaches 0 definition. So the next thing to figure out is what's the function? What function are they talking about? And so here, it's pretty clear that they're asking you to take a square root of something, right? In this case, it's just x. Because when they plug in f of a plus h, they get the square root of 9 plus h. So the function they're referencing is just the square root of x, right? So now that we've identified what the function is and what the fixed point is, the thing that we know that they're asking for is f prime at 3. No, at 9, not 3. Your fixed point is 9, sorry. And you can always check your answer because this should be f of a, right? Does f of a give us 3? Well, if I plug this 9 into my function, is the square root of 9 3? Yes, right? All right, so B, same idea. First, identify what A is. What are they adding to H? What's A in this case? A is 1, right? What's the function? What function are they replacing with 1 plus h to give them this expression? Yeah, 1 over x. And then so to us, it looks like they're asking for f prime at 1. We can verify that because this should be, that should be f of 1. And if we plug in 1 to the function that we said it was, we'd get 1 over 1, which is 1, right? So this is our answer. All right, the last one I threw in there just because it's important that you're able to recognize when they're using the alternative version of derivative, this second version, which was actually the first version that we defined. But here, they're actually using that one. They're letting x approach a. So what's a in this case? Yeah, a is 0. You can see it here, you can see it here, right? That's a, that's a. And then this one's much easier to extract the function out of. What's f of x? Yeah, it's just cosine. And then what they're asking for is our derivative at point 0, right? So there's our answer for that. Working backwards. So listen. That's it for 2.3.